So, the first topic I'd like to talk about are sets of numbers. These are the various types of numbers that we use in math. The first number, or the first set of numbers I'd like to talk about, are called the natural numbers. Now, as a kid, we first learned to count. So these numbers are also known as the counting numbers. And we counted with 1, 2, 3, etc. Now math builds upon itself. The next group of numbers that we learned were called the whole numbers. Since math builds upon itself, we're going to include the natural numbers. But in addition to that, we're going to add on the 0. So we start now with 0, 1, 2, 3, etc. The next group of numbers that I'd like to talk about are known as the integers. The integers are where the negative numbers come into play. So, we're going to now talk about -3 and -2 and -1. Notice 1, 2, 3 are natural numbers. So we call these the negative natural numbers. And then, of course, here's our 0. And then 1, 2, 3 are counting numbers that we learned as a kid. Notice what we have not spoken about yet. We have not spoken about fractions or decimals. These come into the next group of numbers, which are known as the rational numbers. Rational numbers are certainly fractions. And rational numbers are known as decimals. But here's what you need to understand about decimals. Decimals are actually divided into 3 categories. 2 of the categories are considered rational. So, let me get back to a fraction. 1/2 is clearly a fraction. Well, if it is considered rational, then its decimal counterpart needs to be considered rational as well. So, the decimal version of 1/2 is 0.5. If 1/2 is rational, so is 0.5. Let me talk about another fraction. Let's say 1/8. Since 1/8 is rational, then its counterpart is also rational, 0.125. Notice these 2 decimals, they just naturally stop on their own. They naturally terminate on their own. The first group of decimals that are considered rational are those that just naturally stop, naturally terminate on their own. Let me get back to a fraction. How about if I talk about the fraction 1/3? That's a fraction. Since it is rational, its counterpart, its decimal counterpart, needs to also be considered rational. If you recall, the counterpart to 1/3 is this repeating decimal of 0.33333. It just keeps on going forever and a day, doesn't it? This second group of decimals are decimals that are considered repeating decimals. They never stop, but they do have some kind of pattern to them. And so since they don't stop, we call them non-terminating decimals. So, 2 groups of decimals are considered rational. Why? Because their fractions are considered rational. Another group of numbers are the irrational numbers. Now, this is where our third group of decimals comes in. These irrational numbers are contrary to the rationals. The rational says they naturally terminate. The rational says they also repeat if they don't terminate. So, this third group is a non-terminating group of decimals, but since it's non-terminating, it can't be repeating. because if it's repeating, it's rational. So this one has no pattern to it whatsoever. There is one very infamous decimal that we all know, and that is pi. Pi is equivalent to 3.1416 blah blah blah. It keeps on going forever and a day. It never stops, but it doesn't have a pattern to it either. So this is considered an irrational number. Another type of number that's considered irrational are those non-perfect square roots. For example, the square root of 2. So this in its decimal format is 1.141, etc., etc., etc. It doesn't stop either. And I could give you a whole list of other non-perfect square roots, and if you look at their decimals, they'd never stop. The only reason they stop is because we run a display screen on our calculators. Now, let's talk about the last group of numbers. The last group of numbers are known as the real numbers. Here's the interesting thing. The real numbers aren't a new set of numbers. The real numbers hold these 5 together. The real numbers are the natural numbers to the irrational numbers. All those 5 groups of numbers above are all considered real numbers. Now, let me give you a visual representation of the sets of numbers. We first learn to count with our natural numbers. They're the heart of everything. If you notice, the natural numbers are also in the whole numbers. They're also in the integers. And by the way, can a natural number be considered rational? Well, if it can, then you could write it as a fraction. Can't you write 2, which is a natural number, as a fraction? Since you can, it's also considered rational. So, the rational numbers, the natural numbers can be found in all of these first 4 sets of numbers. So they're at the heart of our whole number system. The next group of numbers that came into play are the whole numbers. Now, the whole numbers are just a little bit bigger than the natural numbers. You're like, yeah, but it's only bigger by 1 number. It doesn't matter. It's a bigger set, even if it's only by 1 number. So, the whole numbers include the naturals, and they're a bigger set of numbers. The next group of numbers are the integers. Notice within the integers, I've got the whole numbers because there's the 0 and there are the naturals. So they're just a little bit bigger, actually a lot bigger, than the whole numbers. So the integers include the whole numbers, and they also include the natural numbers. We call the natural numbers a subset of the whole numbers. But the natural numbers are also a subset of the integers. It just means they're a smaller set. Now, our next group of numbers are the rational numbers. They include fractions and they include decimals. We just spoke about being able to write a natural number as a fraction, which means that's an even bigger set. And we use Q for rational. Now, here's the interesting thing. These irrational numbers, notice, They are the third group of decimals. They do not include natural numbers because natural numbers are rational. And if you're rational, you can't be irrational at the same time. The irrational numbers are off in their own little world. They don't want to associate with anybody. They're loners, they're lone wolves, they're socias, whatever you want to call them. They just want to be left alone. So they're off in their own little world, which is why we have the real numbers. The real numbers hold both these worlds together, and we use a double-lined R for real. So, how you doing so far? Good? Now let's talk about some examples. Let me give you some numbers, and let's talk about which group that they would be part of. Let's talk about these particular numbers. So, let's talk about the number 5 first. I want to know which group of numbers the number 5 falls into. First off, if I look at the natural numbers, I don't see any negatives in the natural numbers, so it can't be there. If I take a look at the whole numbers, again, I don't see any negative numbers in there. If I take a look at the integers, this is where I see a negative. So I know for certain that the negative 5 is definitely considered an integer. Now let's see if it belongs to anything else. Can negative 5 be considered a rational number? In other words, can you write negative 5 as a rational number? Can you write it as a fraction? And if you're not sure, let's think about this. If you write negative 5 as negative 5 over 1, that is definitely a fraction, which means it will also be considered a rational number. Let's take a look. If it's rational, can it be irrational at the same time? I hope you said no, because remember, the irrational numbers are not part of any of these 4 groups right here. So it can't be considered irrational. But it can be considered real also because the integers and the rationals are in this universe known as the real numbers. So it would also be considered a real number. Cool. So negative 5 belongs to 1, 2, 3 sets of numbers. Got it. Now, let's talk about the 6. If we look back, 6, that is one of our counting numbers, so it would definitely be a natural number. Since it is a natural number, let's look at our chart over here. Since 6 is a natural number, then by this chart, it also is a whole number, it's an integer, and it's a rational number. Because it can write it as a fraction, 6 over 1. Would it be considered an irrational number? No, because this is its own little world, irrational. It doesn't associate with these 4. But remember, anything in either of these 2 worlds would also be considered real. So that means 6 is a natural number, it's a whole number, it's an integer, it's a rational number, and it's a real number. It belongs to every group except the irrationals. Okay, how you doing? So far so good? Let's talk about this 1/7. Okay, well so far that's pretty easy because since it's a fraction, we automatically know it's a rational number. That's the first place a fraction appears, is in the rational number world. And if I take a look again, at my diagram over here, since it's a rational number, it's at the outer edge of this particular world, which means there's only one other group it can belong to, and that's the real numbers, this whole Milky Way system, so to speak, that universe. So it only belongs to two groups, the rationals and the reals. Let's take a look at the square root of 7. Now, you can get on your calculators and figure out the square root of 7. If you do that, you'll notice that the square root of 7 is a is a decimal that goes on forever and a day. The square root of 7 is approximately equal to 2.64575 blah blah blah. Don't be too impressed, I use my calculator. Now, since it is a decimal that keeps going, but do you notice it doesn't have any pattern to it whatsoever? And if I even take a look beyond the 5 here, it's 1, 3, 1, 1. It definitely doesn't have any pattern to it. So if I notice, irrational numbers have decimals that don't stop and they have no pattern whatsoever, which means this is our first example of an irrational number. But remember, it will also be considered a real number because it's part of that universe. Okay, let's look at the last one. The last number we're going to look at is this 0.2. Clearly, it is a decimal, and I have a decimal that just stops. There's no going on. It just is 0.2 and that's it. So if we look back, those decimals that just stop on their own, naturally terminate, are considered rational numbers. So this one is definitely a rational number, and it is also a real number because it is part of that particular universe. So how we doing? So far so good? Loving it. Let us now talk about properties of numbers. Okay? And not just any old numbers, real numbers. And as we saw, real numbers include 1, 2, 3, 4, 5 different sets of numbers. So, our properties of numbers. The first property I'd like to talk about is the commutative property. Commutative property is like a mirror. You look at yourself in the mirror, you have a reflection. By the way, we have our different operations as well, correct? We have addition, we have subtraction, we have multiplication, we have division. Now, the commutative property says this: if I take 3 plus 5, which we all know is 8, is that the same as 5 plus 3, which is also 8? Clearly the answer is yes. So the commutative property tells me that if I add two numbers in one order, I can reverse the order and get the exact same answer. And by the way, if you notice, we said that this works under the addition operation. Now, does that work for subtraction? If I say 3 minus 5, is that the same as 5 minus 3? Clearly the answer is no, so it doesn't work for subtraction. Does it work for multiplication? If I say 3 times 5, is that the same as 5 times 3? Clearly the answer there is yes, which means for the operation of multiplication, the commutative property works. And I can say multiply the numbers in this order and reverse it over here, and I get the exact same answer. Okay, wait, we have one more to figure out. If I do 3 divided by 5, is this the same as 5 divided by 3? The answer is no. So subtraction and division, both no on that. It just doesn't work. We don't get the same answer regardless. Okay, let's talk about another property, and the next property is known as the associative property. So here's the deal with the associative property. The associative property says I keep order, but I regroup my numbers. You're like, what does that mean? Well, let me give you an example. If I take 2 plus 3 plus 5, would this be the same if I kept the order the same, but instead of adding 2 plus 3 first, if I added 3 plus 5 first, would I get the same answer? Well, let's check it out. You know as well as I do, according to the order of operations, we do parentheses first, which means I'd have 5 plus 5 on this side and I would get 10. And over here on the right side, I do parentheses first, which means I'd have 2 plus 8. And I would also get 10. And yes, these guys are equal. So, the associative property works for addition. I keep the numbers the same order on both sides of the equal to sign. What I do is I regroup. So I'm going to take the first two numbers on the left and I'm going to take the last two numbers on the right. Now, do you think this works for subtraction? You're right, it does not. Do you think it'll work for multiplication? Yeah, it will definitely work for multiplication. Again, I keep the order the same on both sides. The only thing that changes is my grouping. I'm going to group these first two numbers on the left and the last two numbers on the right. Do you think this works for division? No. These properties of real numbers only work for addition and multiplication. So how you doing? So far so good? Loving it. All right, now let's talk about the identity property. The identity says, let's talk about addition, that if I take a number, what can I add to it to get itself back again? Well, if you said 0, you're right. So in this particular case, the number that you would add to any number in order for it to get itself back again is 0. 0 is considered the identity for addition. If I take a look at multiplication, the question is, if I take a number, what can I multiply it by to get itself back again? And if you said 1, that's correct. So 1 is considered the identity for multiplication. All right, one more we're going to talk about. We're going to talk about the distributive property. Now, here's the cool thing about the distributive property. The distributive property combines the addition and multiplication operations. So, for instance, if I'm given this problem, one way I can tackle it is I can add the b plus c first and then multiply by this a. But if I have a problem that looks like this and I can't add inside the parentheses, then I need to think of another way to do this problem. And the other way to do this problem is, as you already know, take the number on the outside and I get to distribute it. I get to multiply it to each of the numbers inside. And then I'll finally add the two answers together. Make sense? Cool. All right, so let's work on some identifying or rewriting of these different properties. So for instance, if I give you something that looks like this, 100 plus x, and I ask you to rewrite it using the commutative property of addition, that means that you would look at the commutative property, and if it's of addition, that means you're going to reverse the order on it. So instead of saying 100 plus x, you will switch the order and say x plus 100. If I give you this particular problem and ask you to rewrite it using the associative property of multiplication, if you go back and you take a look, the associative property of multiplication says the order on the left and the right are exactly the same. The only thing that moves are the parentheses, which means in this particular case, you will maintain the order and it's still multiplication, but now what you're going to do, instead of grouping the 4 and the x, you're going to group the -3 and the 4 instead. How you doing? So far so good. Does that make sense? Cool. What about if I give you this particular problem and I ask you to work this out using the distributive property? Well, according to the distributive property, I'm going to do 4 times A, I'm going to do 4 times B, and then I get to add them together. But here's the interesting thing about this particular property. If I now give you this instead, and I ask you to use the distributive property, you might say, well, I don't see any parentheses. It's already distributed. Well, you would be correct, but notice something. Both of these have an R in common, don't they? And the cool thing about these properties is if you can go forwards, you can go backwards. So I'm going to rewrite this problem and I'm going to put parentheses back in. And I'm going to notice that they distributed the R. So I'm going to take out the R, and when I take out the R, I notice that what is left is the 13 minus 4s. So the original distributive problem that it came from was this one right here. Does that make sense? Cool. Okay, now I want you to identify the properties. So here's the first one that we're going to work with. Now, ask yourself this question. Did the order remain the same on both sides, or did it switch? If you're like, well, it switched, if you notice, which one does the switching? Is it commutative or associative? Correct. It's the commutative property, which means this is definitely the commutative property. Now, is it with respect to addition or multiplication? Well, I don't see any addition sign, so it has to be of multiplication. All right, let's look at another one. If I take a look at I want to know which property this works with, which property this represents. Well, if you notice, they took the 8 and they multiplied it to the 9x, and they also multiplied it to that 3, which means this is definitely the distributive property. Okay, how about this one? Okay, pay close attention. Don't let this fool you. Did the order remain the exact same on both sides? This is BAC, this is ABC. I don't see it being the exact same on both sides. What I notice is the C is in the same place, but I'm noticing the A and the B switched. So remember, if something is switching order, is that commutative or is that associative? You're right. It's the commutative property. So this one is also the commutative property, and it's with respect to multiplication. How we doing? So far, so good? Cool. Loving it. Okay. One last thing that I do want to make certain you remember is how to average numbers. Average involves two operations. It involves addition and division. So this is extremely helpful when you are trying to average your exam scores to figure out what your grade is in the class. If I give you this particular group of numbers and I ask you to average it together, so I'm going to give you these numbers right here, 3, 4, 5, and 8, and I'm asking you to average them. Well, averaging says first thing we're going to do is we're going to add them together. After we add them, we're going to divide by how many numbers we added. Well, how many numbers did we add? You're right, we added 4 numbers. So I'm going to divide by 4. And when all is said and done, let's see, that's 12, that's 12, and there's another 8, that's 20, divided by 4, my average is 5. By the way, it doesn't matter the order in which you add your numbers, right? So by the way, 5 is actually what kind of number? It is a natural number, it's a whole number, it's an integer, it's a rational number, right? And it's also a real number. Okay, I know, they didn't ask for that, but I'm just kind of throwing that in there as a sidebar. Hey, you never know. That's all I'm saying. Let's do another example. If I give you these particular numbers, 45, 33, and 52, and I'm asking you to average these numbers together, which means first thing you'll do is add them. Second thing you'll do is divide. What am I going to divide by? Well, how many numbers are you adding? You're adding 3, which means you'll divide by 3. And when all is said and done on this, you end up with this repeating decimal. And I'm going to remind you of this little bar that they put over the 3, which tells me it keeps repeating. I end up with this repeating decimal as my average. Now here's the deal. If they ask you to identify that, which category of numbers does this represent what category of numbers does a repeating decimal represent? Well, no decimals in here or natural whole. It's in the rationals, and it's in the repeating and non-terminating. It's the second category, which means it would just be considered a rational number, and then it would also be considered a real number. So if they ask you for that, you've got that identification also. So let's just mark that down just to make sure you have it. The 5 is a natural number. It's a whole number. It's an integer. It's a rational number, and of course it belongs to that universe of real numbers. This repeating decimal is a rational number and a real number. It only belongs to 2 categories. So, how you doing? So far so good? Cool. Loving it. See you on the flip side.